Salam, peace be upon you. My name is Muhammad Layak Sadiqi, the father of holophase. Part 36. Prediction as forward constraint in Phi Pattern dynamics. We began by placing pattern before object. We learned that only relations are public, that identity is invariant equivalence, and that boundaries and topology matter. We discovered that change is lawful transformation, that time is derived from transformation order, and that next is certified adjacency. We saw that the physical world is expressed pattern, that the observer is a pattern system inside reality, that measurement produces traces, that memory stabilizes them, and that modeling builds internal proxies. All claims must declare type, scope, window, and provenance. The moment we ask, what do we do with models? We have come so far together. We have learned that patterns are primary, that only relations are public, that identity must be certified, that boundaries and topology shape everything. We have seen how change happens through lawful transformation, how next is not a temporal given, but a certified adjacency relation. We have discovered that the physical world is expressed pattern, objects as stabilized bundles, particles as defect families, fields as distributed descriptors. We have understood that we, observers, are not outside the pattern world, but are ourselves pattern systems, with our own windows, memories, and histories. We have traced how measurement creates traces, how memory stabilizes them, and how we build models, internal proxies that track selected structure of other patterns. Now we face the next question. What do we do with these models? We predict. Prediction is not magic. It is not prophecy. It is not seeing into a pre-written future. Prediction is forward constraint, using the internal patterns we have built to narrow the space of what can lawfully come next. At any moment, a pattern can transform in many lawful ways. Call the present state S, and let LS be the set of all lawful continuations from S. Without a model, LS may be enormous, a vast field of possibility. With a model M and declared conditions C, we compute a subset, LSMC, the continuations consistent with both the laws of pattern transformation and the specific structure of our model. Prediction is the move from LS to LSMC. We narrow, we constrain. We do not create the future, we delimit it. We are not claiming certainty, we are carving the future into allowed and disallowed zones. A simple everyday example, the boiling kettle. Consider a kettle of water on a stove. Without any model, the future is wide open. The water could boil, freeze, turn to wine, disappear. All imaginable, but only some are lawful. With a model of thermodynamics, we predict. When the temperature reaches 100 degrees Celsius at 1 atmosphere pressure, boiling will occur. We are narrowing possibility. We are saying, under declared conditions, this specific transformation is what the laws permit. If boiling does not occur, something is wrong. Perhaps the pressure is not 1 atmosphere. Perhaps the thermometer is miscalibrated. Perhaps our model scope has been exceeded. We are at high altitude, where water boils at lower temperature. Perhaps a hidden variable, like dissolved minerals, is altering the boiling point. Failure becomes information. Every mismatch teaches us something about the model, the conditions, or the world. Another example, the weather forecast. When the forecast says 60% chance of rain tomorrow, it is not claiming that rain is written in destiny. It is saying, given current data D, model M, and boundary conditions B, the lawful continuations distribute such that rain occupies 60% of the measure space. This is measure over branches. From part 29, we learned that stochasticity is disciplined uncertainty about lawful branching. Prediction quantifies that discipline. The forecast is forward constraint. It narrows our expectations without claiming certainty. We might take an umbrella, a rational response to the narrowed possibility space. If it does not rain, the prediction was not wrong in any simple sense. It was probabilistic. The outcome fell within the 40% chance of no rain. The prediction succeeded in its own terms. But if it fails to rain day after day when the forecast said 60%, that pattern of failure becomes diagnostic. It tells us something is off with the model, the data, or the way probabilities are being assigned. Prediction is not prophecy. This point is so important that we must dwell on it. Prediction is not prophecy. Prophecy claims to see the future as fixed and foreordained. Prediction does nothing of the sort. Prediction is structured anticipation based on a model of how things work, current conditions and access, declared scope, and uncertainty bounds. When we predict, we are not claiming to know what will happen. We are claiming that, given what we know, the future is constrained in certain ways. This is humility, not arrogance. It says, here is what we can expect within these limits, under these assumptions. Outside those limits, we do not claim anything. Types of prediction. Not all predictions are the same. We can distinguish several forms. Exact prediction. The model determines a unique continuation. There is only one lawful next state consistent with model and conditions. Example, a total solar eclipse at a specific second. Celestial mechanics is so precise that we can predict the exact moment when the moon will completely obscure the sun. Bounded prediction. The future lies within a range. The continuation set is constrained but not unique. Example, tomorrow's high temperature will be between 18 and 22 degrees. We cannot say exactly, but we can bound. Probabilistic prediction. The continuation set carries weights. Each possible future has a measure attached. Example, 60% chance of rain. The forecast assigns probabilities to different outcomes. Conditional prediction. If condition X holds, then Y must follow. Example, if you heat water to 100 degrees Celsius at sea level, it will boil. The prediction is conditional on the antecedent being true. Each type has its own structure, its own uncertainty, its own way of being tested. Each must be declared as such. 6. What prediction depends on? Predictions are not free-floating. They depend on several factors, all of which must be declared. Model fidelity. How well does the model track the invariant structure of its target? A high-fidelity model yields sharper predictions. Access resolution. What can we measure? Finite windows limit precision. We cannot predict what we cannot see. Target stability. Is the predicted pattern stable or does it amplify small differences? Chaotic systems, like weather, have fundamental limits on predictability. Uncertainty accounting. Are the error bars realistic? Overconfidence is a form of dishonesty. Condition accuracy. Garbage initial conditions produce garbage predictions. If our measurements of the present are wrong, our predictions of the future will be wrong too. Prediction is never independent of these factors. A good prediction declares them. 7. A cosmic example, orbital motion. The equation F equals ma compresses constraint. From gravitational law, F equals g of m1 and 2 divided by r squared, we can predict the motion of planets. Given current position and velocity, the next position is tightly constrained. This is exact prediction within a declared scope. When deviations appeared in Uranus's orbit, they were not treated as failures of Newtonian mechanics. They were treated as diagnostic information. They pointed to the existence of an unseen planet, Neptune. The mismatch revealed hidden structure. Failure illuminated what was missing. Prediction, even when it fails, guides discovery. Another example, the chess grandmaster. In chess, from a given board state, lawful continuations are finite but numerous. A grandmaster's internal model, built from years of experience, narrows the field dramatically. They do not compute every branch. They constrain by pattern recognition. Their predictions are about which moves are worth considering, which lines are promising. If an opponent makes a surprising move, mismatch occurs. That failure updates the grandmaster's model of the opponent's strategy. Prediction, mismatch, revision. This is how skill develops. Prediction and its scope. No prediction exists without scope. Scope includes time window. Over what duration does the prediction hold? Spatial domain. Where does it apply? Initial conditions. What is the starting state? Boundary conditions. What are the edges of the system? Access limits. What can we measure and at what resolution? Regime validity. Under what conditions does the model hold? Newtonian mechanics predicts planetary motion well at moderate velocities. At speeds near light, it fails. Not because it is wrong, but because its scope has been exceeded. Special relativity takes over. Prediction without scope declaration is incomplete. It is like a map without a scale, unusable. A biological example, the immune system. The immune system predicts pathogen behavior. Memory cells encode prior encounters. The prediction, if this pathogen reappears, immune response will activate rapidly and specifically. If the response fails, if the pathogen has mutated, that failure is diagnostic. It tells the immune system that a new variant is present, triggering adaptation. Prediction, failure, and adaptation are not just scientific activities, they are the very mechanisms of life. Failure as illumination. Now we come to one of the deepest lessons of part 36. Failed prediction is not failure of science, it is illumination. When a prediction fails, when the actual future lies outside the predicted range, that failure is structured information. It tells us something specific about where our understanding is incomplete. A failed prediction can reveal model inadequacy. Our model may be missing key variables, wrong about relationships, or poorly calibrated. Scope overreach. The prediction may have exceeded the model's valid range. The model works elsewhere, but not here. Hidden variables. Something we did not account for influenced the outcome. The failure points to what is missing. Genuine stochasticity. The system may be inherently unpredictable at this level. The failure teaches us about the limits of predictability. Boundary condition errors. Our initial conditions may have been wrong. The failure points to measurement error. Wrong prediction type. We may have claimed exactness where only bounds or probabilities were appropriate. Failed prediction is not a dead end. It is a clue. It guides model revision, scope refinement, and deeper understanding. 12. Historical example, the Ptolemaic system. For centuries, astronomers used the Ptolemaic model to predict planetary positions. It worked reasonably well, but had persistent errors. Predictions failed in small but noticeable ways. These failures were not just annoyances, they were diagnostic. They revealed that something was wrong with the model's fundamental structure. Eventually, these failures led Copernicus, Kepler, and Newton to better models. The geocentric system gave way to heliocentric, circular orbits to elliptical, mysterious epicycles to universal gravitation. Failed prediction drove progress. 13. Another example, the financial crisis. Economic models failed to predict the 2008 financial crisis. Many models showed no possibility of such an event. They assigned it near zero probability. The failure was diagnostic. It revealed hidden variables, systemic risk, interconnectedness, shadow banking. Model inadequacy, assumptions of efficient markets, normal distributions, rational actors. Scope overreach, models calibrated on calm periods failed in crisis. The failure taught economists what they had missed. It led to new models, new regulations, new understanding, though whether the lessons were fully learned remains an open question. Prediction as computational constraint. We can now state the principle formally, but in plain language. Let S be the present state of a pattern. Let LS be the set of all lawful continuations from S, all the ways the pattern could lawfully change. Let M be our model, an internal pattern that tracks selected structure of the target. Let C be the declared conditions: window, scope, initial state, boundaries. Prediction computes. P equals subset of L of S consistent with M and C. The actual future F, when it arrives, can be compared to P. If F is in P, the prediction is confirmed within bounds. If F is not in P, we have a mismatch, diagnostic information. This is the structure of prediction. It is not mystical. It is computation inside pattern reality. Prediction and the derived quantities. Our earlier understanding of probability, energy, and entropy as derived readouts now connects directly to prediction. Probability is measure over lawful continuations. It is what we use when we cannot predict exactly. Probabilistic prediction is the honest acknowledgement of branching under finite access. Energy is a ledger that remains invariant across transformations. Conservation laws are prediction engines. They tell us what cannot happen. If energy is conserved, any predicted future that would change total energy is ruled out. Entropy measures multiplicity under coarse graining. High entropy systems have many microstates consistent with our macro description. This limits prediction. We cannot know which microstate will be realized. Entropy quantifies our predictive limits. Prediction lives at the intersection of all we have built. An engineering example. The bridge engineers predict the load a bridge can bear. Using stress equals force over area, material properties, and structural models, they compute maximum safe load. The prediction is conditional. If load exceeds threshold, failure occurs. When the Tacoma Narrows Bridge collapsed in 1940, the failure was diagnostic. It revealed that the models had overlooked aerodynamic resonance, wind-induced oscillations that amplified beyond structural limits. The failure taught engineers something new. Bridge design improved. Prediction, even in failure, advances knowledge. Prediction and identity. Prediction must preserve identity discipline. The observer who predicts may update their models, but they must remain the same observer for the prediction to be meaningful. If updating destroys identity invariance, the system ceases to be itself. This is why we have persistence. Part 20. The observer persists through change, maintaining core identity while revising models. Prediction and identity are linked. We predict as the same self that will experience the outcome. The continuity makes learning possible. The rigor layer, the prediction gate. Every prediction claim must pass a gate. The prediction gate asks, is the prediction type declared, exact, bounded, probabilistic, conditional? Is the scope specified, time window, spatial domain, initial conditions, boundaries? Are uncertainty bounds provided? Error bars, confidence intervals, probability distributions? Is the model dependence declared? What model generated this prediction with what fidelity? Are success/failure criteria defined? What would count as confirmation? What as falsification? Is prediction distinguished from prophecy? Is it clear that we are narrowing possibility, not claiming certainty? If any of these are missing, the prediction claim cannot be certified. It is incomplete. Firewalls. Prediction discipline installs several firewalls. No prophecy. We do not claim to see the future as fixed. We only constrain possibility. No hidden uncertainty. Every prediction has uncertainty. We declare it. Overconfidence is dishonesty. No model-free claims. Predictions come from models. We declare which model and its limitations. No unscoped universality. Every prediction has a scope. We declare it. No failure denial. When predictions fail, we do not hide it. Failure is diagnostic. We learn from it. No undefined success criteria. If we cannot say what would count against the prediction, it is not testable. These firewalls keep prediction honest. What prediction gives us? By the end of part 36, we have installed several understandings. Prediction as forward constraint. We know that prediction is about narrowing possibility, not seeing the future. Prediction types. We distinguish exact, bounded, probabilistic, and conditional predictions. Prediction dependence. We know that prediction depends on model fidelity, access resolution, target stability, uncertainty accounting, and condition accuracy. Failed prediction as diagnostic. We understand that failure is information, not embarrassment. The prediction gate. Every prediction claim must pass this gate. Connection to the framework. Prediction integrates with stochasticity, adjacency, energy, entropy, identity, and persistence. Refusal conditions. We refuse a prediction claim if scope is missing, no time window, no spatial domain, no conditions. Uncertainty bounds are absent, no error bars, no confidence intervals, no probabilities. Model dependence is hidden, no indication of what model generated the prediction. Success-failure criteria are undefined, no way to test the prediction. Prediction is treated as prophecy, certainty claimed without basis. Refusal is not punishment, it is protection, ensuring that prediction claims are meaningful and testable. Why this matters beyond science? Prediction is not only for laboratories, it is for how we live. Every decision we make involves prediction. Will this job make me happy? Will this relationship last? Will this investment pay off? Will this choice lead to a better future? These are predictions, forward constraints based on our models of ourselves, of others, of the world. They are always scoped, always uncertain, always model dependent. They can fail. And when they fail, that failure is diagnostic. It tells us about our models, our assumptions, our blind spots. Prediction discipline in life means knowing that our predictions are not guarantees, acknowledging uncertainty, nothing is certain, treating failure as information, not as personal defeat, updating our models based on what we learn, remaining humble about what we can foresee. The future is not a script, it is a branching field of possibility. Prediction is how we navigate it, not with certainty, but with constrained expectation and the readiness to learn. A closing image, the ship's navigator. Imagine a ship's navigator in the age of sail. They have charts, models. They have sightings, measurements. They have a sense of currents and winds, conditions. They predict, if we maintain this heading, we will reach port in 3 days. This is not prophecy. It is forward constraint based on what they know. If they encounter an unexpected storm, the prediction fails. That failure is not a sign that navigation is useless. It is information about the storm, about the limits of their models, about the need to adjust. They adjust, they learn, they sail on. We are all navigators. The future is our ocean. Prediction is our chart. And every mismatch is a lesson that makes the next chart better. The handoff from prediction to learning. We now have prediction, forward constraint based on models. But what happens when predictions fail? A system that can update itself in response to failure can learn. Learning is identity-preserving adaptive change in response to mismatch. That is part 37, updating. How a Phi pattern learns without ceasing to be itself. This has been part 36 of the Phi Pattern Science Foundation. The journey continues with part 37, updating. How a Phi pattern learns without ceasing to be itself. Always, peace be upon you.